Friends, hope you all are doing good. Welcome back to third session of quantitative analysis, complexometric titrations. So, titrations involving complexing agents are known as complexometric titrations. These complexing agents are coordinating with the metal ions through different donor atoms and forming very stable complexes. Let's understand what are complexes. What is complexes? So complex consists of a metal ion surrounded by the molecules or ions. So these molecules or ions are called ligands. So ligands are the species which are donating its lone pair of electrons to the center metal atom, and metal is accepting those lone pair of electrons from ligands. Now complex is formed by the combination of metal ion with the electron donating group or nucleophile, right? So here I am giving example, that is copper complex. So Cu2 plus, that's the metal ion, and ammonia donates its lone pair of electrons to the copper. Four ammonia is donating, each ammonia is having one lone pair, is donating its lone pair of electrons to the copper and forming four coordinated complex, right? See here, square planar complex is formed here. So each ammonia donates its lone pair of electrons to the center metal atom. So here ammonia is a complexing agent, and metal is accepting electrons from the complexing agent and forming complex. And complexes are compound formed by the combination of metal ions with the ligands, complexing agents. So ligands are known as complexing agents actually here. So the metal ions and electron deficient species. Metal ions are electron deficient species, while ligand is electron rich. So that's why metal accept electrons from the ligand, and thus electron donating species. A metal ion will thus accept electrons from a ligand where the coordinate bond is formed. Electrons forming coordinate bond come surely from the ligands, right? So that is about a complex. So how complex are formed? So ligands donating its lone pair of electrons to the metal, and metal accept because metal is electron deficient species, and ligand is electron rich species. So electron is capable and preferable to donate its lone pair of electrons, its electrons to the center metal atom, that is metal atom. Metal accept electrons from ligand and forming a coordinating bond, right? So that coordinating bond from the direction from ligand to metal. So that's what it's saying, right? A ligand is called monodental ligand if it is donate a single pair of electrons. Here ligands are classified into based on density. So what is density here? So number of lone pair of electrons to the donated to the center metal. If the ligand donates its one lone pair of electron to the center metal atom, that is monodental ligand. So mono means one, so one lone pair. So one lone pair donated to the center metal atom. If it is ligand having two lone pair of electrons, if it is donated those two lone pair of electrons to the center metal atom, that ligand is called bidentate ligand. Okay, so that means it having two donor sites. Next, if it is having three lone pair of electrons, that means three donor sites, so that ligand is called tridentate ligand, and tetradentate, pentadentate, and polydentate. All these are ligands are polydentate ligands. And EDTA I am giving here, ethylene diamine tetraestic acid, right? It is a hexadenal ligand. So that means it having 6 donor sites. So 4 oxygen atoms and 2 nitrogen atoms here. So ligand can be as simple as ammonia, which forms a complex with the copper 2 plus, forming the giving complex CuNSO 2 plus, right? So this is copper complex. Here ammonia is monodental ligand because it is having only one lone pair of electrons. That means each nitrogen having one lone pair of electrons. Here 4 ammonia is donating 4 lone pair of electrons to the center metal atom and forming coordinated bond, and then forming complex, copper complex, blue color complex. So when ligand is a large organic molecule having 2 or more complexing groups like EDTA, the ligand is called chelating agent and formed by the complex, in this case called a chelate. So here a new term, that is chelating agent. You know complexing agent. So complexing agent is it's donating it form complex with the metal ions. So one kind of complexing, that is here chelating agent. So chelating agent also complexing agent, but is a strong complexing agent because it having more than 2 donor sites, right? More than that means 2 or more of the complexing groups, that means more donor sites donates more lone pair of electrons to the center metal atom, forming a ring type structures. So that means chelate. So chelate means here ring, forming ring type structures with the metal ions. Okay, so and this complex are called and these ligands are called chelating agents. That means those ligands are forming ring type structures with the metal ions are called chelating agents, and those complexes are called chelates, right? Now I am giving here a few examples. Tridental ligand, that is diethylene triamine. You know, ethylene diamine, EN, NH2, CH2, CH2, NH2. That is ethylene diamine. Ethylene diamine having 2 lone pair of electrons. 2 lone pair of electrons on 2 nitrogen atoms. So it is bidental ligand, and that was example for bidental ligand. Now it is 3-dental ligand. That means tridental ligand. It having 3 lone pair of electrons. That means it having 3 donor sites. See here, 3 nitrogens, NH2 having 1 lone pair of electrons, CH2, and NH2 nitrogen having 1 lone pair of electron again, and CH2, NH2. So there you have to write NH2, right? Only one hydrogen I am writing here. You have to correct it, that NH2, that is NH2. So NH, first one is NH2 and last one is NH2, and middle one is NH. So by satisfying its valency 3, right? So here having 3 nitrogen atoms, so these 3 lone pair of electrons donate to the center metal atom and form a 5-membered ring. So that type of ring structures are called chelates. So it is a chelating agent, right? And next, tetradentate ligand. So tetradentate ligand means tetra means 4. So 4 donor sites it is having. So this triethylene tetraamine. So this triethylene tetraamine, which was indicated by triene. So it is a tetradentate ligand because it having 4 lone pair of electrons. These 4 lone pair of electrons donate to the center metal atom and forming chelates. So it is also a strong complexing agent. And hexadentate ligand is a very strong complexing agent, and this was used in the complex titrations because it is a strong complexing agent, forms very strong complexes with the metal ions. So it was used in complex titrations. So if you see that here CH2 both as NH, N, CH2, N. In both nitrogens having 2 lone pair of electrons. So 2 lone pair of electrons from 2 nitrogen atoms, and again 4 acetate groups. If you look at that terminal acetate group, CH2COO minus and CH2COO minus. So last oxygen, that is having extra lone pair of electron, that is 3 lone pair of electrons. Out of these 3 lone pair of electron, 1 lone pair of electron can be donated to the center metal atom. So 4 oxygens are available here. So 4 oxygens are donating its 4 lone pair of electrons, and 2 nitrogen atoms donating its 2 lone pair of electrons to the center metal atom and forming a strong complexing agent, that is a hexadentate ligand. Because it is having 6 donor sites, it is known as hexadentate ligand, strong complexing agent. So this is very important, EDTA. Here I am giving a few complexes, Ag center metal atom and 2 cyanide. Cyanide is anionic ligands. Ligands are also classified based on the charges also, neutral ligands and anionic ligands and cationic ligands. If over the species, if you are having negative charge, that is a anionic ligand. Over the species, if you are having positive charge, that is cationic ligand. No charge, that is a neutral ligand, like CO, H2O, NH3. All these are neutral ligands. Cn minus, halogens, OH minus, SO4 2 minus. All these are anionic ligands. And NO plus, nitrosonium, hydrogenium, NH2, NH3 plus, hydronium, H3O plus. All these are cationic ligands, right? Most probably neutral ligands and anion ligands are forming complexes with the center metal atoms, that means metal ions, right? So if you see that here Ag plus and Cn minus, cyanide is a monodentate ligand. So here cyanide is another special type of ligand, that is ambidentate ligand. So what is ambidentate ligand? So it is having more than 1 donor site. Of course it is a monodentate ligand, but that donor site either side, either here, if you see that here cyanide, if it is nitrogen having a capability to donate its lone pair of electrons, carbon also having capability to donate its lone pair of electrons. If you write here cyanide, so it is a lone pair of electron from nitrogen. If you write NC isocyanide, where carbon will donate, right? This is the amidan ligands like NCSCN minus and NCS minus. Also amidan ligands NO2 nitrate and ONO, that is also NO2. So here nitrogen will donate and or oxygen will donate. So that is also amidan ligands. That's these are the amidan ligands about. So here I am giving examples of forming complexes. The metal ion acts as a Lewis acid. Yeah, you know, because metal ion accept lone pair of electrons. The species those species which are accepting lone pair of electrons those are called Lewis acids, and the ligands are used as a titrant or complex forming agents which act as a Lewis bases, right? So they are negatively electron paired on negatively charged groups. Now complexometric titrations. Complexometric titration is a technique of volumetric analysis in which a soluble and dissociated stoichiometric complex are forming during the addition of titrant to the sample solution. So here having metal solution and here having complexing agent. Now these two are adding and forming complexes. Okay, so these complexing agent are forming reacting with the metal and forming complex, right? Very strong complexes. So in complexometric titrations, the formation of a color complex is used to indicate the end point of the titrations, right? So complexometric titrations are particularly useful for the determination of mixture of different metal ions in the solution. If a solution having different ions, for example hardness of water, calcium, magnesium, if you have more than one metal ions in a solution, these complexometric titrations are very useful to determine the metal ions, right? And an indicator capable of producing a definite color change. So we are having different metal ion indicator. We discuss all the metal ion indicators. So here EDTA titrations. So what is EDTA? So I told you now, EDTA is a hexadentate ligand because it is having a 6 lone pair of electrons. Ethylene diamine tetraacetic acid. It has a 4 carboxyl groups and 2 amine groups. From 4 carboxyl groups, it donates 4 lone pair of electrons from 4 oxygen atoms and 2 lone pair of electrons from 2 nitrogens. See the structure here. So this is a hexadentate ligand. Now different forms of EDTA. So if the pure form, that is ethylene diamine tetra, if it is EDTA present in ethylene diamine tetraacetic acid, that is having low solubility. It is insoluble in water because the organic compounds is insoluble in water. But if you are having a disodium salt, 2 hydrogens are replaced by the 2 hydrogens are replaced by 2 sodium, that is disodium salt of EDTA. So that is more used, that is soluble in water. So that one is used for our titration. So EDTA has a 4 carboxyl groups and 2 amine groups. So EDTA is a polydentate ligand as it is donate its 6 lone pair of electrons of for the formation of a coordinate covalent bond with the metal cations to form metal EDTA complex. See the complex structure. So this is the structure of EDTA. And after reacting with the metal, it form a metal EDTA complex like this, right? See here a complex structure, metal EDTA complex, here forming a 5-member ring. If you observe a 5-member ring here, so they are forming chelates, right? So role of pH in indicator titrations. So EDTA titrations are carried out in a buffer solution of metal ions to be estimated. So the use of proper pH is important and it is related to the stability constant of metal EDTA complex. So here it is very important to maintain the pH during the EDTA titration, right? Because the hydrogens are dissociated because in carboxyl group we are having CH3COH, that hydrogen H plus ions dissociated, then only oxygen must be dissociated, then only oxygen donates its lone pair of electrons to the central metal atom. And also mostly complexes are forming in basic condition, so that's why maintaining pH 7. So you must maintain the specific pH for the formation of complexes, right? So advantages of EDTA as titrate. So why you are using EDTA in forming complexes? So EDTA forms stable complex with the various metal ions because EDTA is a strong complexing agent. So it's not ETTA, it's EDTA. Just correct it. So EDTA form very strong complexes with the various metal ions. The complexation occurs in a single step, and hence the titration of metal produces sharp change in the metal ions concentration at the equivalent point. So it occurs in a single step, the formation of complex in a single step. So we can observe sharp end point. Okay, sharp color change you can observe at a end point. So that's the second one. The metal EDTA complex are very complexes are all water soluble. So metal EDTA complexes are water soluble, so no problem for solubility. Hence all studies can be performed in a aqueous media. So EDTA forms 1:1 complex with all metal ions. So one molecule of that, if you're taking one zinc molecule, it requires one EDTA, right? So it forms a 1:1 complex with the set metal ions irrespective of all charge on the metal ions. Stoichiometry is same for all metal ions. The reaction can be represented as like this here. So H2 Y2 minus, that means that is the EDTA, Mn2 plus, and forming Y, here Y is your EDTA, MYN minus 4, right? So this is the advantages of EDTA. Why EDTA is because why EDTA is a strong complexing agent, because it having 6 lone pair of electrons. It has 6 lone pair of electrons to the center metal atom, and forming a chelates with the metal atoms forming ring type structures, and hence forms strong complexes, and it that complex is occur in a single step. So sharp endpoint was observed, and metal EDTA once formed the complex. All these metal EDTA complexes are water soluble, so all you can perform in aqueous media, and EDTA forms 1:1 complex. So these are all advantages of EDTA used as a titrant. Now, so theory of metal ion indicators. So what happens? What is the principle actually? So principle of complexometric titrations. Now, if we are having so let us take a conical flask. In conical flask, we are having a metal solution. Now adding indicator, right? So adding indicator, metal indicator plus EDTA, so forming metal EDTA solution, right? Metal EDTA plus indicator, because metal indicator and metal EDTA. So if you compare these two, so metal EDTA is a strong complex when compared to metal indicator. Indicator also a complexing agent here. So all metal indicators are strong complex, all complexing agents. They form complex with the metal ions. Okay? So initially a metal indicator complex will be formed. So after titrating with the EDTA, so this indicator would be replaced by EDTA and forming metal EDTA complex by separating out indicator. So this reaction takes place only if the metal EDTA complex is more stable than a metal indicator complex, right? So metal indicator first, the first step formation of metal indicator complex. After formation of metal indicator complex in conical flask, now you are titrating with the EDTA, which is taken in the burette. So while adding EDTA from burette, what happens? This indicator would be replaced by EDTA and forming metal EDTA complex. Where all indicators replaced by EDTA, you can observe there. You can observe color change. That's your end point. So examples of metal ion indicators. Let's see. Heliochrome black tea. This is strong, very frequently used metal indicator, heliochrome black tea. So generally called as EBT. EBT indicator, that means heliochrome black tea. So that's it. This is your structure. This is your EBT structure. Chemically, it is sodium salt of 1-hydroxy 2-naphthalazole 6-nitro 2-naphthol 4-sulfonic acid. A very long name. Just see the structure. Observe, right? So it is a dark powder. It's a dark powder, and it is having a blue color. A blue color solution, right? While it is reacting with the metal, they form metal EBT complex. Metal EBT complex is wine red. Metal EBT complex is wine red. So just add EBT to the complex to the metal solution. They form metal indicator. The metal EBT complex. The metal EBT complex is wine red. So when it is titrating with EDTA, they form that EDTA replace this indicator and forming metal EDTA complex by separating indicator. The indicator color is blue color. So at the end point you can observe blue color. So wine red to blue color is your end point when you are using EBT as your indicator, right? So EBT used to estimate the magnesium, zinc, manganese, cadmium, mercury, lead, copper, aluminum, ferrite, titanium, cobalt, nickel, and platinum. So most of metal ions are determined, estimated by this EBT indicator. The indicator is prepared. How this EBT indicator can be prepared? Let's see. The indicator is prepared by dissolving 0.2 grams of EBT powder in 15 ml of triethanolamine, followed by the addition of 5 ml absolute alcohol. Right. In this way, you can prepare the EBT indicator. Next type of indicator, muir oxide indicator. So this is also widely used while you are estimate the calcium, magnesium, cobalt, zinc, cadmium, copper, metal ions in EDTA titration. This the indicator is prepared by dissolving muir oxide powder. So it is a powder, pink, I think brown color powder it is. In water, aqueous solution muir oxide is unstable, hence it must be prepared freshly. It is a solid indicator. Muir oxide is a solid indicator. EBT is a liquid indicator. So here next types of titrations. Types of titrations. Complexometric titrations generally 5 types. Out of 5 types, generally 3 are most important. That is the direct titrations, indirect titration or back titration, direct titration, back titration, replacement titration. These 3 are the different types of complexometric titrations. So first one, direct titrations. So what happens in direct titrations? How it was performed? See, this is the direct determination of a metal ion by adding standard ETA titrate to the sample. So this is the direct. The name itself indicates direct. Right. So direct titration means in burette you are taking a EDTA solution. In conical flask you are taking a metal ion solution. Let's say zinc sulfate. So if you are taking zinc sulfate solution in conical flask, just add a EBT indicator to this conical flask solution. They form zinc indicator complex. That zinc EBT complex firstly formed, that is wine red. So just wine red color complex is formed. After that, this wine red complex, zinc EBT complex, titrating with the EDTA which was taken in burette, just this EDTA indicator which is present in conical flask was replaced by EDTA from burette. They forming metal EDTA complex. That is after all replacing this indicator molecules by EDTA, at that point you observe a blue color. So that's your end point. So this is direct titrations, right? The solution contains the metal ion is buffered to the desired pH. You must add, you don't forget to add buffer, because you have to maintain the pH, basic pH, okay, basic condition, pH 10. That's where you're adding ammonia hydroxide, ammonium chloride buffer. That must be added, right, during titration. Some auxiliary complexing agents such as tartaric acid can be added to prevent the precipitation of hydroxide of metal ions, copper plus 2, zinc 2 plus, nickel 2 plus. Sorry, nickel 2 plus can't be estimated by direct titration. It can be estimated by back titration. Just remove that. Copper, zinc can be determined by using this direct titration method, right? Calcium, magnesium also determined by this direct titration method. And back titration method. So this is the method. An excess of standard ETA is added to the sample solution of metal ion. So back titration method is performed when complexation is very slow, complexation is very inert, or suitable pH, that is suitable indicator, is not available for that complexation. So in those conditions, you are not performed directly with the direct titration with the EDTA. So in that case, you have to perform back titration. So what is back titration? So this is the method. An excess of standard EDTA is added to the sample solution of metal ion, right? So first, for example, nickel. So nickel sulfate solution. So when I estimating nickel, you are using this back titration method. So firstly, you are taking in conical flask, burette, conical flask, nickel sulfate solution. for example, taking 20 ml of nickel sulfate solution and then add excess of EDTA, that means 40 ml of EDTA solution is taken in a conical flask. So 20 ml of nickel sulfate solution and 40 ml of EDTA solution, excess of EDTA solution. Now this mixture, now add a metal indicator, that is EBT indicator you have to add, and add a buffer solution to maintain pH, right? Next, now this mixture is titrated against to standard solution like zinc sulfate solution, which is taken in the burette, right? Now titrating against zinc sulfate solution. Here you can observe back titrated with the zinc sulfate solution. Here you can observe the endpoint reverse. In the first case, direct titration method, you can observe a wine red to pale blue. Here you can observe pale blue to wine red. So this is the back titration method. So in this back titration method, aluminum, cobalt, lead, manganese, mercury, nickel, tubeless can be determined by using this back titration method. So actually what happens in back titration method? So first, which one is not directly reacting with this EDTA, that means very slowly reacting this EDTA complex that was taken in your conical flask, then add excess of EDTA solution. So EDTA complexing with this metal ion, because of here adding excess of EDTA, so some amount of EDTA is consumed to form that particular complex. Now this mixture, the remaining after formation of complex with this metal ion, then this complex mixture react titrating with the standard zinc sulfate solution. Now zinc is fastly forming complex with the EDTA solution. Now some portion of EDTA in conical flask, they forming complex with the zinc EDTA complex, right? So where you can observe endpoint, that is wine red, where complex form, that is zinc EDTA complex is one. So the remaining portion of the excess of some portion of zinc metal ion, some portion of EDTA forming complex with zinc, and the remaining portion of EDTA would be formed complex with the nickel sulfate, that is nickel, right? So that in the so that can be calculated by using some few calculations, where in this way you can calculate the estimate the amount of nickel or manganese, lead, cobalt, nickel, aluminum, right? So this is about back titration. And the third type of titration, that is a replacement or displacement or substitution titration. This is a measure weak EDTA complex of another metal. So one metal ion, they form weak EDTA complex. So they form complex with the EDTA very slow, that means very weak EDTA complex of another metal ion is added to the solution of metal ion to be determined, that is M1. This is strong complexing metal, strong complexing with the EDTA. So Mg EDTA and zinc EDTA are the frequently used weak EDTA complex, right? So the weaker metal EDTA complex is replaced with the stronger metal EDTA complex. That's why you are carrying, call it as a replacement or displacement titrations. The equivalent amount of metal M2 freed from the weaker complex can be titrated with the standard EDTA solution. This method is used for the determination of calcium 2 plus ions, right? Use of masking and demasking agent. So masking agent, so what is masking agent and demasking agent? So masking agent act either by precipitation or by formation of a complex is more stable than the interfere ion EDTA complex. Masking is the process in which a substance is prevented to take part in the reaction without physical separation of it. So reagent used to mask is known as masking agent. That reagent, particular reagent is known as a masking agent. So what is masking agent? So if you are having a 2 or more, if you are having 3 metal ions in a solution, now you are determining individually. Now we have to mask one, right? So in that case, we are adding a reagent, that is masking agent, which forms precipitation with that complex, which forms reaction with that only particular metal ion. That means that particular reagent masks that cation. So that reagent is called masking agent, right? Here I am giving masking by precipitation, right? So many heavy metals, example cobalt, copper, lead can be separated either in the form of insoluble sulfides using sodium sulfide or insoluble complex using thioestamide. So these are filtered, decomposed and titrated with the disodium mediator. So other common precipitating agents are sulfate for lead and barium, oxalate for calcium lead, and fluoride for calcium magnesium lead, and ferrocyanide for zinc and copper. So 8 hydroxyquinone for many heavy metals, right? So thioglycerol is used as a masking copper by precipitation in the assay of lotion containing copper and zinc, right? Now demasking, so the exactly reverse. So once mask that particular metal ion by masking agent, next after the next step, now you have to determine that metal ion. Now before determine that, you have to demask. So that masked agent must be demasked. That means you have to release that particular metal ion. So in that case, you have to add a demasking agent. So in this technique, the one of the cation must be masked and remaining free cation is titrated with the standard EDTA. So then previously masked cation is demasked by using suitable agent to get free cation. So this free cation is then titrated by using standard EDTA, right? Formaldehyde or chloral hydrate and methanol acetic acid mixture 3:1 used to demask the cyanide complex of cadmium and zinc. If you are having cadmium zinc, formaldehyde used to demask the one of the metal, that is zinc. Let's say an example. So formaldehyde is used to demask the zinc cyanide complex. So initially, so zinc was masked by cyanide, that is we are forming zinc cyanide complex here. Now we are adding demasking agent formaldehyde, so that was free this zinc from this complex, zinc cyanide complex Geren 2 plus. So this free Geren 2 plus ion then titrated by using standard EDTA solution, as it is possible to determine the zinc in the presence of calcium, right? So these are the masking, this is about masking and demasking agent, right? So this is about complexometric titrations. This is the first principle of complexometric titrations and metal indicators, EBT, mur oxide and fast sulfur black F, right? Indicators you must know, and maintain pH to maintain basic condition while performing this complexometric titrations, and different types of complexometric titrations, direct titration, back titration, and lastly replacement or substitution titrations, right? So this is all about complexometric titrations. Thank you. In the next class we are discussing about fourth titration, that is precipitation titrations.